So I tried my best to make it work in landscape. It didn't work out, so we're going to have to do it in portrait mode. Because if I make the board landscape, the life is refusing to work in to capture it in landscape mode. Instead, tell me to reorient my screen. So, but that shouldn't be a problem. Yeah, good evening. So for now, you guys are just about 4 people. So let's wait until it reaches about 10, then we can kick off. I just hope the I students are here because the tutorial, I think they're going to benefit from us starting from the beginning. And even for those of you in undergraduate that missed the beginning, this will be an opportunity for you guys to catch up with the parts you missed out on. For those of you that missed out on the first class we did online. So we're waiting for you guys to get to number 10. These are just 8 people. Okay, so I think we can start now. Please, is there any ICE student that is currently live so that we know that you guys have representation here? Because it seems like most of the people that are responding are from UTME. Okay, you guys are here. Okay, so I think we can start. So in this tutorial, when we are done, you are going to understand the concept of probability generating function. That's PGF for short. So if I mention PGF, we're also talking about probability generating function. And we're also going to construct and use the PGF for given distributions. We're also going to use formulas for the mean and variance of a discrete random variable in terms of its PGF, which is short for probability generating function. And we're going to use these formulas to calculate the mean and variance of a given probability distribution. We're also going to use the results that the PGF of the sum of independent random variables is the product of the PGFs of those random variables. So I'm here to teach that in class, but eventually we're going to get there. So, like I told you guys already in class, the major difference between PGF and MGF is that whereas moment generating functions has to do with uniform distributions, not uniform, continuous distributions, PGF has to do with discrete distributions. So some of the examples we are going to look at are binomial, geometric, and Poisson distribution, and the discrete uniform distribution, because uniform can either be discrete or continuous. So we're going to be looking at a discrete uniform distribution example. But before we go into distributions, let's look at a very basic example of a probability distribution, so that at least we can have an idea of what we are talking about even before we start looking at advanced distributions. I just hope the I students are here because this tutorial is majorly for them, because I know I's alone are way more than 8, because I can see only 8 people watching. And the whole idea behind this tutorial is so that they can catch up. Even a lot of you guys in UTME that are missing classes, this is also meant for you, but this is the kind of number I'm getting. I don't know. Somebody is saying it's still portrait. Yeah, but now the board is also portrait. Do you understand? The reason why we couldn't work with the last one was because the board was in landscape and the video didn't want to change to landscape. It was in portrait. But now that the board is in landscape, is in portrait also, it's, do you understand? It's easy for you to grab everything, unlike before when it was in landscape. So now that it's portrait and the video is portrait, I think it balances out. So let's start with an example so that we can kick off and get an idea of what we are working with. So let's look at this example. We have number of goals, frequency, and relative frequency. So we have 0, we have 1, we have 2, we have 3, we have 4, we have 5, and we have greater than 5. So the frequency is 149, 179, 91, 37, 3, 3, and 0. Then the relative frequency is 0.323, 0.381, 0.197, 0.080, 0.06, 0.06, and 0. This is to 3 decimal places. So this is all starting from scratch, from the very beginning. This is all starting from the very, very beginning. So when we talk about relative frequency, what are we talking about? We're talking about the rate of the frequency to the total frequency. And in English, not just calculation, that means probability or the chance of the team managing to score certain goals during the game. So this probability distribution table because it shows all the individual probabilities with respect to the discrete random variables. So I believe so far so good. We have not done anything out of the ordinary yet. So this same table can be represented algebraically. So how do we do that? We introduce G of t. And this G of t, we use it to represent the function. We generalize a function to represent the probability distribution and the relative frequency. That's what we use G of t for. So if we were to apply this G of t to this table that we generated, what do we get? We have 0.323 times t raised to power 0 plus 0.38. Is this 1 or 7? Let me confirm. Sorry, I think that's 1, not 7. Abi? I'm coming, I think it is 7. This is 7, not 1. So 7 raised to power 1, t raised to power 1, plus 0.197 times t raised to power 2, plus 0.080 times t raised to power 3, plus 0.06 times t raised to power 4, plus 0.06 raised to power t raised to power 5. No need to represent this because 0 will cancel it out. So far so good. We have not done. Okay, somebody asked that we should please come again on what we use G of t for. So G of t is actually the probability generating function. So what does that mean? That actually means that we are just using a general expression to represent the probability distribution with respect to its relative frequency. That's simply what it is. I know for now we're not dealing with any specific distribution per se, like Poisson, uniform, what are their names, geometric, and so on and so forth. So this is just like a general example, so I can have an idea of how it works. So note the okay, do we need to, okay, no, for now let's pause with this. So the probability is the coefficient of the polynomial function. That's probability is the coefficient of the polynomial function, and the function we created is the probability generating function, PGF. Did you get that? The probability is the coefficient of the polynomial function, and the function we created is the probability generating function, PGF. Now, this is a polynomial function used to represent the probability information. This is the polynomial function used to represent the probability information that we extracted from the table. Now, why is this important? We know that all probability distribution must satisfy the expression summation P of x equals to x equals to 1. So let T equals to 1, then G of 1, meaning this probability generating function where T is 1, is equals to summation of x equals to x, where x can be 0, 1, 2, 3, 4, 5, and okay, in this case we are stopping at 5 because 0 will take this out. So now, based on this, we know it must always equal 1. So let us check. When you add 0.323 plus 0.387 plus 0.197 plus 0.80 plus 0.06 plus 0.06. I don't even know what I should say. You guys should add it. I don't know if that's how we are going to do it, but if you add this, you're going to get 1. So that may satisfy the condition that summation of the probability of x is going to give you 1. Now, where is this used? We can use the PGF to get the sum of any probability distributive function. So for example, now this table now, we can write it in form of the PGF. So let's convert this our table to PGF form. So to convert it to PGF form, this will turn to T of x. This will turn to probability of x equals x. And last but not the least, we'll have T of x times P of x equals to x. So once we do that, what is going to happen? This will turn to T raised by 0, T raised by 1, T raised by 2, T raised by 3, T raised by 4, T raised by 5. So in this case, we don't need this again. Hope you are taking note of how things are changing. We don't need that again. While for the bottom, there are some little changes that will take place here. There's some little changes that will take place here. So now, the first one is what? T raised by 0 is 1. So 1 times whatever you have here will repeat itself, which in this case is what? Oh, sorry. This will also change. This will also change. Because we're now working with the probability, not just the frequency. So now the probability is what? 0.322. If you remember, that's what we had here. If you remember before in the former table. 0.387, 0.197, 0.080, 0.06 and 0.06. So that's the probability from the former table. So now, what will be our T of x times the probability? So T raised by 0 is 1, so 1 times this will give you the same thing. Now T raised by 1 times 0.37 will give you 0.387 times T. Now T raised by 2 times 0.197 will give you what? 0.197 times T raised by 2. T raised by 3 times 0.080 will give you what? 0.080 times T raised by 3. Same with this 0.06 times T raised by 4 and 0.06 times T raised by 5. Now, if you look at this, what does this remind you of? Reminds you of this. Reminds you of this. So now, in order for us to generate the PGF, we can get the sum of the products probability generating function between T raised by x and its individual probabilities. So what does that mean? Sorry, I'm coming. I think one of my notes is missing. Geometric. Binomial Poisson. Can you snap your notes? Anybody's note that is complete, what we have next, so that I can confirm that I have the right material here. Just give me some minutes. I'll be back. Can you ask me how you change the values in the table? Yeah, I'll come back to that. I just want to make sure my material is complete. But please, before I get back, help me snap your notes. Let me confirm that I have the next page here. So I think a page is missing. I think a page is missing, but I'll find a way to make do. So what this showed us is, okay, you said, where is that person's question? You said, can you explain why you changed the values in the table? So, it's PGF we're looking for. So that initial table, something to switch off. So that initial table was for that, was like the raw data you get. Oh, the scored goals, what's the frequency of the goals scored, what's the relative frequency. So all of that is what we changed into our probability generating function, like we converted the data. And that's why I took time to explain step by step how we were able to achieve that. So maybe I'll just go through that one more time before I clean the board. So like I told you, after we created that table, let me see if I can find where I addressed that. So after we created a table, the ratio of the frequency to the total frequency what was here before, if you remember. For example, before we had frequency here. So for example, if you had 149 and you add all the frequency, if you remember before, there was 149 here, there was 179, there was 91, 37, 3, 3, and 0. So if you add all of that, the ratio of 149 to the total ratio is 0.322. So I don't have a calculator here with me. Let me see if I can get a calculator so that we can just, because that's why this is a tutorial. Whatever we're doing, you have to make sure you understand, because that's what differentiates it from a class. So I'm with the calculator now. So let us add the total frequency from before. If you remember the frequencies here. So let's add them. We had 149 plus 179 plus 91 plus 37 plus 3 plus 3. So 149. Sorry, where did I? I'm not used to this calculator. 149 plus 179 plus this calculator plus 179 plus 91 plus 37 plus 3 plus 3, which is 462. So if we check 149 that was here before, that will be 149 divided by 462, which is 0.322. Do you understand? Yeah. Don't know if I'm addressing T with Jade podcast. That's the person I'm addressing. That's what's making me go back to this. So if you add the frequency, the total frequency, each frequency relative to the total frequency was how we got our relative frequency. So if you check that relative frequency, that is also our probability eventually. Do you get? So that's why we could change this table, change the random variable to the T, became our independent variable. Then the probability was our frequency. Do you understand? Then our PGF is this random variable times the probability, which is what? T of x times P of x. And that's how we got 0.322 times T raised by 0. T raised by 0 is 1. So 1 times this will give you this. And the rest, as you can see, this is 0.387 times T raised by 1, and so on and so forth. So that's how we got that. So I don't know if you understand now. I understand now. Okay. Okay, so I think we can move on from there. I think we'll move on from there. I think we can move on from there. I'm still looking for, there's something that is missing before we start solving questions. Let me see if I can get it from here. So before we move into question solving, you will notice that G of t is equals to what? Summation of probability of, have I written this already? I think so. T of x, p x equals s, which we have shown in our table, which is the same thing as the expectation of t of x. So take note of this. So what this means is that G of t is equals to E of t of x. By definition. So take note of that. So now we're going to look at each uniform distribution on that PDF. We'll solve questions, then we'll also see how to derive them. So let's start with the first one, which is discrete uniform distribution. So let me clean this. So now we have the question. Let x be the discrete random variable. Let x be the discrete random variable that denotes the score when a fair die is thrown. Find the probability generating function for x. So this will be x one, two, three, 4, 5, 6. Who can tell why we're working with 1, 2, 3, 4, 5, 6 in the comment section? I'm going to say the answer, but before I say it, you can tell me why we're working with 1 to 6. Anybody? Yes, somebody got it. This person said, because it's a die. Sir, can I please come again with the quote? Which quote is that? With the question. Okay, what question? What question is that? Because the die has 6 faces, correct. Dice is actually plural. So the correct was actually die. Oh yeah, Najite, what is the question? The one the table is for. Are you referring to the former question or what? If you're referring to the former question, what is your question. Like if you're referring to the former table, or is it this table you're talking about? So I think I'll move on so that once you ask your question, I can address it. Because the die has 6 faces, correct. So the reason why this table has 1 to 6, one number to 6, is because a die has 6 faces. So who can tell me what distribution this is going to be? What is the PG? What is the probability going to be for each face? Oh, okay. You didn't get the question. Okay, so I'm going to go over the question again. Let X be the discrete random variable that denotes the score when a fair die is thrown. Find the probability generating function PGF for X. I go over that one more time. Let X be the discrete random variable that denotes the score when a fair die is thrown. Find the probability generating function PGF for X. So somebody has actually answered it correctly. Uniform because they have the same probability, correct. So this is an example of discrete uniform distribution, because when you throw a die, the chances of you getting 1 is 1/6. Chances of you getting 2 is 1/6. Chances of you getting 3 is 1/6. Chances of you getting 4 is 1/6. Chances of you getting 5 is 1/6. And chances of getting 6 is 1/6. So it's uniformly distributed. So if you remember, this is how we denote uniform distribution. And what is the chance? 1/6. So we can see our K is equal to 1/6. Now, to find our PGF, if you remember, just like that former example, we work with G of T. Now, what is our G of T going to be? You multiply this by this, all through. So the first one will be what? T raised by 1 times 1/6 plus T raised by 2 times 1/6 again, and so on and so forth. This will be 1/6 times T raised by 1 plus 1/6 times T raised by 2 plus 1/6 times T raised by 3 plus 1/6 times T raised by 4. 1, 2, 3, 4 over 6 times T. Sorry, should be plus here. Plus 1/6 T raised by 5 plus 1/6 T raised by 6. So this will give you what? 1/6 will come outside, such that you will now have, okay, you can make it 1/6 T, because 1/6 T is in all of the equations. So you are left with 1 plus T squared plus T raised by 3 plus T raised by 4 plus T raised by 5. So now, if you look at this thing very well, you realize that this is a geometric series. So if you remember correctly from geometric series, the first term is A and the common ratio is T. So if you remember, sum of a geometric series is what? Sn, the formula A 1 minus R raised by N over 1 minus R. In this case, our R is equal to T and our A is equal to 1. So if we are to rewrite this equation, since our first term is what? 1/6 T and our R is T, we have 1/T raised by 6 because our N is 6 and 1 minus T. But just to make sure what we solved is correct, don't forget there's a way we can check. How do we check? From what I taught you some minutes ago, we check with G of 1, which must always equal 1. So let's put 1 in our T and see if we are going to get 1. 1/6 times 1, 1 minus 1 raised by 6, 1 minus 1. So in this case, you have 1/6 times 0, which is undefined. Undefined. So what does this tell us? This tells us that something is wrong somewhere because we're supposed to get 1. So meaning we have to recheck what we did here, because this did not produce 1. So I took time to show that in case you are solving a question and you don't get 1. So it's not like it is wrong, it's just that we need to find out if there is something we missed. So we bring back this 1 minus t. This is where we stopped, if you remember, from this, using our a equals 1 minus r over 1 minus r. Hope there is no problem so far. Okay, no problem. So if you look at this thing very well, what did you notice about this? We can write this as 1 over 6t times 1 minus t squared raised power 3, true or false? Because 2 times 3 is 6, which is same thing as what? T raised power 6. And this can be written as 1 raised power 3. Because anything raised power 1 raised power 2, 1 raised power 3, 1 everything is to give you 1. So 1 minus t. Pay attention to what I'm about to do now. From algebra, you know that when you have a raised power 3 minus b raised power 3, this will give you what? A minus b times a squared plus ab plus b squared, true or false? So if we are to rewrite this in this form, what is it going to give us? We're going to have 1 minus 6t, 1 minus t squared, because in this case our b is t squared. So take note. Then we have what? 1 squared plus 1 times our b squared, which is what? T squared plus t squared squared. Okay, all divided by 1 minus t. Now, 1 minus t squared is the same thing as 1 squared minus t squared, true or false? Because 1 squared is still the same thing as 1. So if we open 1 squared minus t squared, this will give us what? 1 minus t times 1 plus t times 1 squared plus t squared plus t4. So what did you notice? 1 minus t we cancel out. Don't forget 1 minus 6t is still outside. So once this cancel out, what are you left with? You are left with 1 minus 6t, 1 plus t times 1 plus t squared plus t4. So let's now try that our check again. Let's put g of 1 and check if we get 1. So this 1 times 6 times 1 times 1 plus 1, which is 2, times 1 plus 1 plus 1, because 1 squared is 1, 1 to the raised power 4 is 1. So this is what? 2 times 3 times 1 over 6. So this will give you what? 1 over 6 times 6. Cancel, cancel. This is 1 over 1. Our g of 1 is equal to 1. So that shows that our working was correct. Sir, please can you do the algebraic expression again, but a bit slower? Okay, I'm going to do that. But most of all, I found the note I was looking for. I actually found that note that I was talking about. So After we solve this, we'll go back to that note. It's just about a page, so it's not like a note per se, because I was supposed to address that page before coming to solving examples. So I'll go over this one more time, then we'll go to that page that I was looking for because I found it. So from the question, we know the three-way die, and a die has 6 sides, and the probability of getting each side is 1 over 6, 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 1 over 6. So this is an example of discrete uniform distribution. So that's why we wrote it this way. But even if I've addressed that page before now, you would have understood how we arrived at this. That's why I said we'll need to go back for other distributions so that you can understand. So once we write it like this, because our key is equal to 1 over 6, so you write it with this U representing uniform distribution. We need to get our PGF, which will represent to G of t, if you remember. So this table can be written as what? T raised to power 1, T raised to power 2, T raised to power 3, T raised to power 4, and so forth, such that our G of t will now be our T times our probability distribution, which is what in this case? 1 over 6 times T raised to power 1, 1 over 6 times T raised to power 2, 1 over 6 times T raised to power 3, plus 1 over 6 times T raised to power 4, plus 1 over 6 times T raised to power 5, plus 1 over 6 times T raised to power 6. So if you look at this thing very well, what did you notice? 1 over 6t is in all of this. So if you bring out 1 over 6t, you have what? 1 plus t squared plus t raised to power 3 plus 3 raised to power 4 plus t raised to power 5. And if you notice, if you multiply 1 over 6 times t times any of this, you get this back, because 1 over 6t times 1 is 1 over 6t raised to power 1. 1 over 6t times t raised to power 5 is 1 over 6 times t raised to power 6. So once you bring it out like this, what did you notice? You will notice that this is a geometric series. So once it looks like this, the sum of a geometric series is what? A times 1 minus r raised to power n over 1 minus r. And when we tested to find out if what we did was correct, we put g of 1 into that, and we found out that we got undefined. So it's looking as if what we did was not correct, but we know what we did should be correct. So we now look at, is there something we can do with this sum of geometric series to arrive at our answer? And the answer is yes, because if you look at this very well, you will notice that this t raised to power 6 can be written as t squared raised to power 3, because 2 times 3 is 6, which is same thing as t raised to power 6. And this one can be written as 1 raised to power 3. So this can be written as this, nothing else will change. And from algebra, remember that a raised to power 3 minus b raised to power 3 is same thing as what? A minus b times a squared plus ab plus b squared. So once you have this, all you have to do is slot in your values. Our a in this case is 1, don't forget. A is 1, b is 3, t raised to power 2. Because a3, 1, 3, 1, b3, our b is what? T squared. So that's how they got that. So when you slot in the values, you have what? 1 squared minus t squared times 1 squared plus 1 times t squared plus t squared squared, once you slot in all the values. So you remember that 1 square minus t square, we can make that 1 square, because 1 square will still give us 1. Don't forget, this square was not there. I was one that added it, because when you put in, where is that in? When you put in 1, yeah, it's just 1 or not squared. But we added the square, because 1 square is same thing as 1. Hope you haven't forgotten. This square was not here. If you put 1 here, there's no square. But the reason why we put square is because 1 square is the same thing as 1. Why did we put square there? Because 1 square minus t square is same thing as 1 minus t times 1 plus t. So 1 minus t will cancel 1 minus t. So you're left with, don't forget, 1 over 6t is outside. So you are left with 1 plus t times 1 square plus t square plus t raised to power 4. So once we bring it to the side, we have 1 plus t times 1 plus t square plus t4, 1 over 6t. So this is our expression. So to find out if this is correct, we have to find g of 1, because g of 1 must equal to 1, don't forget. So slotting our values, 6 times 1 is 1 over 6. 1 plus 1, because t will now become 1, is 2. 1 plus 1 square plus 1 raised to power 4 is the same thing as 1 plus 1 plus 1, because all these things will still turn to 1. So this is the same thing as 1 plus 1, 2, 1 plus 1 plus 1, 3. 2 times 3 is 6. So this will give you 1 over 6 times 6. 6 cancels 6. You are left with 1 over 1. So our g of 1 is equal to 1. So that shows that our expression was correct. So does it mean we must always test with 1 after g of t, sir? Yes, you have to test to confirm that what you did was correct. To confirm that what you did was correct. So can I clean and move on? Because I need to go back to that page that I missed out on. Should I proceed? Are we done with this? Yes, okay. This one that is about me that is saying yes. Any other person? Before we move on, is there any other person? Should we carry on or does anybody? I understand now. Thank you, sir. Okay, so we'll go back to the page I have been looking for. What is the time now? So I don't. 9:22. Wow. So I want to link the former page to this. So if you remember, when we were solving that first example and we got to the new table that now had t of x, and we explained that t raised by x ranges from t raised by 0 to t raised by 5, and how the probability of x replace the relative frequency. Then we now showed how the PGF is actually t raised by x times p of x. So the next thing is PGF, and I know we've already addressed some of this in the question we solved now, but like I said, this page, we also addressed this page before we got there, so I just want to do this so that you are not confused. So our PGF can be written as g of t equals to summation of t of x times p. So it must always look like this. And if you look at this very well, this looks like expectation of x, which is same thing as summation of x p x equals to x. So if you look at this very well, this means that our g of t is equal to summation of t of x p of x equals to x, which is the same thing as expectation of t of x. So let me explain this quickly. Our g of t, we found out it was summation of t of x times probability of x. If you remember that table, that had something like 1, 2, 3, 4, 5, which we changed to our t of x to now be t raised by 1, t raised by 2, t raised by 3, t raised by 4, t raised by 5. And our probability of x, in this case, let's just say 0.1, 0.2, 0.3, 0.4, and 0.5. And we're able to show that our PGF, g of t, was the summation of this times this, t of x times p of x, which in this case will be 0.1 t1 plus 0.2 t2 plus 0.3 t3, and so on and so forth. So that's what they mean by summation of t of x times probability of x. But this also looks like expectation of x, which is what summation of x times probability of x also. So what does this now tell you? This tells you that your g of t is actually your expectation of t of x. I don't know if you got that. Okay, I'm saying yes, sir. So you will notice that your g of t, your probability generating function, is actually the expectation of t of x. So hope you got how that happens, because this fundamentals is what will make you appreciate when we go further, when we start solving specific distributions. So therefore, since this relationship exists, we can relate it to the properties of a probability distribution. What is the second property? First property is g of 1 should give you 1. Take notes. Second property now is g of t. G of t is equal to expectation of t of x. First property, second property. So now, how do we represent all the distribution under discrete? For uniform, this is how we do it. U of k, where x is the uniform distribution with a constant value k, where k can be any real number. So this is represented by x equals to x of k, where k is any real number. So for binomial distribution, this is how we represent it, being n and p. And the probability mass function is equal to summation of n combination x, p raised by x times 1 minus p n minus x, where x is equal to 0, 1, 2, and so on up to n. So what does this mean? This is any discrete random variable that has a number of trials n and probability of success p is its individual probability is given by this formula and it's binomial. So take note of that. Now for geometric, this is how we represent geometric. Geo of p. Now the probability mass function for geometric is what? X equals to x 1 minus p raised by x minus 1 times p, where x equals to 1, 2, and so forth. So when is this used? This is used to represent the number of failures in an event before success is achieved. So if the distribution looks like a case where there will be failures until you achieve success, then you are working with geometric distribution, and this is the PMF. Now, Poisson is represented by this, and the PMF is represented by x equals to x exponents minus lambda under x divided by x factorial, where x is equal to 0, 1, 2, and so on. So, and where lambda is the average value of a certain period of a unit, whatever that unit may be, time, etc. So this is used to study the duration of certain events occurring over a certain period of time. That's when Poisson comes in. So this is the page I missed. I believe there is nothing technical about this. So no, that's, yeah, so please come again on how E of x is E of t of x. Okay, so I'll do that, but before I do that, hope you have any issue on all these distributions and their PMF. So I was saying that our PGF, we've shown from table that it is what? Summation of t of x times the probability of x. And I just showed a small example up here. That if you remember, if we have 1, 2, 3, 4, 5 as an individual variable, and we have the probability of it occurring as 0.1, 0.2, 0.3, 0.4, 0.5, for us to turn into PGF, G of t, this t of x will come here, and t will now carry all these numbers, t raised by 1, t raised by 2, 2 raised power 3, 2 raised power 4, 2 raised power 5. So our PGF is T of X times P of X, which in this case will be what? 0.1 times T plus 0.2 times 3 raised power 2 plus 0.3 raised power 3 raised power 3 and so forth. So summation of all of that will give you our G of T, which is what we have here. Which is what we have here. Now, if you look at expectation is what? Summation of X times probability of X. So they look alike. So if you look at this very well, you realize that our G of T can be written as the expectation of T raised power X. Because instead of writing it as the expectation of X, our X in this case is T raised power X. So that's why we can write G of T as E raised power T of X. So I say, take note of this property. G of 1 must give you 1. That's the first property. And second property is what? G of T is what? Expectation of T of X. So I believe with that, I have covered that. So I think we can move on to the next question. Right, I think we can move on. Please, someone should signify if we should move on. Okay, I get it now. For the rest of what you did, you were proving the PGF for different distributions, right? Not necessarily proving. This is just me showing you the PMF, the probability mass function of each discrete distribution. So it's not like proof. These are the formulas you are going to use when you are solving questions, which we have even solved one. We solved uniform. So if you remember, this was what we used when we solved uniform distribution question. So I believe I can move on, right? Yes, we can. Please give us a few minutes to write. Oh, okay. But I think you guys already have this notes now, already. Oh, I assume you guys already have the notes because this tutorial is assuming that I have the notes. So I just explain what is in the notes. So please, are you saying that G of 1 is the same as probability of X when we are solving for uniform distribution? G of 1 must be equals to 1 is a property. Probability generative function of 1 must always give you 1. So what that implies is that no matter what distribution you are working with, whether it's geometric or whether it's uniform or whether it's Poisson or which other one do we have? Geometric, Poisson, whether it's binomial, if you find the G of 1, it must always give you 1. That's what it means. It must always give you 1. So please believe you are available for replay. Well, I don't know about that. It might not. That's why it's important you attend while it's happening. Attend while it's happening. It's not promised whether it will be available or not. So make sure you attend, because back when I was teaching you guys, I asked you guys, do you want tutorial? And almost the whole class said yes. And now we therefore have up to 20 people in a class of over 100 plus. So it's either people who are not aware of tutorial or they are simply not interested. And if the number is not interesting or not, then I'll assume that people are not interested, you get. So, because I have other things to do with my time. Yeah, sir, please, okay. So I think we can move on. Because this tutorial is absolutely free. In any case, if it was paid, I'll say, okay, maybe people don't have the money or something. This one is free of charge. So It's so funny that even people that are not attending class that you would think we jump on the opportunity, they are not here. You know, so I don't know what to say about that. You would think for people that are not attending class or people that are in class and didn't understand, you would think they would be here. So, can force a horse to stream, can force it to drink. And if why they are not here is they are assuming that it will be available offline. That one is to my own discretion. It might not be available. So, yeah, that's that. So let's move on to another question that we have here. So this question, we have a pack of playing cards contain 52 cards with 13 cards each of 4 suits: hearts, spades, diamonds, and clubs. A card is selected at random from a normal pack of cards. If it is a heart, the experiment ends. Otherwise, it is replaced. The pack is shuffled and another card is selected. Let X represent the number of cards selected up to and including the first heart. Find the PGF for X. Now, if you look at this question, who can tell me what distribution this is and why? Who can tell me what distribution this is and why? Who can tell me what distribution this is and why? You guys are not responding. Hope you guys can hear me. Please, can you guys hear me? Geometric distribution. This one is only Najite that is talking since. Hope the others can hear me. Geometric distribution. So why is it geometric distribution? Oh yeah, why is it geometric distribution? That's what I explained in the last. Because it's failure and success question. Yeah, it's not like you're wrong, but I think there's something you are missing. Have you forgotten that there will be number of, let me see, somebody has said, because there's numbers of failure before success. Yes. I still think there's something you need to say that you haven't said. There's something you need to say. If you remember, for geometric, there will be number of failure before success is achieved. Yeah, so you're right. Has any other person said anything? Rebecca said, because of the possibility of failure before success is achieved. Yeah, so you have all tried. So let's now represent this. So we have X geometric of P, where P is what? 13 over 52. And why is it 13 over 52? There are 13 cards in each suit. So if the card you're looking for is a heart, that means there are 13 hearts. And the total of cards is 52. So that's why our P is 13 over 52, which is the same thing as what? 1 over 4. So since we've got our 1 over 4 and we know that P plus Q will give you 1, Then Q will give you 1 minus P. So 1 minus 1 over 4 will give you 3 over 4. Okay? So don't forget, our probability mass function for geometric is what? 1 minus P x minus 1 times P, where x is equals to 1, 2, and 3. So let us now find for each one probability of x equals to 1 equals to 1 minus 1 over 4. That's why using this 1 minus 1, which is what? 0, times P, which is 1 over 4. So this will give 1 over 4 because this is for 0 is 1. So 1 times 1 over 4 is 1 over 4. If we want to find the second one, x equals to 2. This will be 1 minus 1 over 4. 2 minus 1. 2 minus 1 is 1 times 1 over 4. So this will give you what? 3 over 4 times 1 over 4. And so on and so forth. So if you want to work with the first 5, 1, 2, 3, 4, 5. First one is 1 over 4. Next one is 1 over 4 times 3 over 4. Next one is 1 over 4 times 3 over 4 squared. Next one is 1 over 4 times 3 over 4 cube. Next one is 1 over 4 times 3 over 4 raised by 4, and so on. So our G of t, don't forget, t will come here, then t raised by this, t raised by this, and so on. So when you multiply each one, what would that give you? To be what? 1 over 4 times t raised by 1, which is the same thing as t, plus 1 over 4, 3 over 4 times t squared. What was that? 1 over 4 times 3 over 4 squared times t raised by 3 plus 1 over 4 times 3 raised by 3 times what? T raised by 4 plus 1 over 4 times 3 over 4 raised by 4 times t raised by 5. So we can simplify this. How do you simplify this? All we have to do is bring out 1 over 4t. So we bring out 1 over 4t, you now have 1 plus 3 over 4t plus 3 over 4t squared plus t 3 over 4 t cube plus 3 over 4 t 4, and so on. So what we notice is that this has become a geometric series and it is infinite. So since it's infinite, which formula are we going to use? We're going to use a over 1 minus r, where our a is equal to 1 and our r is equal to 3 over 4t. Our r is 3 over 4t. So now, what do we now do? One of 4t is outside. This has turned to a geometric series. Our a is 1 minus a geometric infinite series. That's why I'm using this formula. 1 over r, which in this case is 3 over 4t. So let's find the LCM of this. 1 in 4 is 4. 4 times 1 is 4, minus 4 and 4 is 1. 1 times 3 is 3. So this is the same thing as 1 over 1. 4 minus 1, 1 over 4. So this is the same thing as 1 over 1 divided by 4, which is times 1 over 4. So this is 1 over. Hope I've not made a mistake. over 1 over 4, okay? So this is same thing as 1 divided by 1 over 4, which is same thing as 1 times 4 over 1. So this will be 1 over 4t times 4 over 1. Abi? Hey, sorry, there's a t here. There's a t here. So this is not 1, no. This is... Sorry about that. Sorry about that. So 4 minus 4, let's go back to this. When you find the LCM as 4, 1 in 4 is 4. 4 times 1 is 4. Minus 4 and 4 is 1. 1 times 3t is 3t. You get, so this is 1 over 4t times 1 over 4 minus 3t over 4, which can be written as 1 divided by 4 minus 3t over 4, which can also be written as 1 times 4 over 4 minus 3t times 1 over 4t. 4 cancel this. So this will be what? 1 over, not 1, t over 4 minus 3t. So let's now do that our test to confirm that this is correct. G of 1 will give you what? 1 over 4 minus 3 times 1. So this will give you what? 1 minus 4 minus 3, which give you 1 over 1, which is equals to 1. So that means this is correct. This answer is correct. Any question? Okay, so I can't find any question. Is there any question before we move on? Any question before we proceed? How is it over 4 minus 3t, sir? How is it? Where do we start that from? But at least you know how we turn this into this, right? Because since this is a infinite geometric series, then we are going to use this formula a over 1 minus r, where our a is 1 and our r is 3 over 4t. So that's up to this point. So this 1 over 4t is here, and we now have 1 over 4t times a 1 over 1 minus 3 over 4t. This is the next stage. And I told you that we can find this LCM. 1 in 4 times 1 is 4, minus 4 in 4 is 1. 1 times 3t is 3t. So that's how we ended up with 1 over 4t times 1 over 4 minus 3t over 4. Now, I told you that if you look at this very well, this is the same thing as 1 divided by 4 minus 3t over 4. True or false? So this division, if you turn into times, this 4 will climb, and this 4 minus 3t will come under, which is what happened here. So 4, we cancel out this 4. So we are left with t. So t times 4 minus 3t will give you what? T over 4 minus 3t. So when you slot in your g of 1, you have what? 1 divided by 4 minus 3, which is 1 over 1, which will give you 1. So there is a mistake. Where? We can process that. Where is the mistake? It's So 1 over 4 t is t over 4. It's t over 4. T over 4, okay. Where are you getting t over 4 from? It's not 1 over 4 t, it's t over 4. T over 4. T over 4. Okay, you're referring to this. Okay, so if it's t over 4, what does that change? Oh, yeah, that's true. That's true. So this is what the person pointed out. Where is our t? This t is t over 4, not 1 over 40. It's as good as t. So hope you understand. It's t over 4, not 1 over 40. This is also t. You can write the t like this. You can write it t over 4, but it's not 40, it's t over 4. And that is why your final answer is t times 1 times 4 over 4 minus 3. Hope you get. Because if it's t, then it's the denominator that we multiply by t. But since it's the numerator, that's why the t is on top. So take note of that change. It's t over 4, not 1 over 40. Times, okay. The value, okay. So I think we have corrected that. So even though we are going to end in geometric, we still need to show. We need to show how we derive our PGF for geometric distribution. So this one doesn't have to do with values, just like a proof. In case I ask you in your exams to find the PGF of a geometric distribution. So with that, we'll close for the night. That we close for the night. Any question? No question. So we all know that g of t is what? Expectation of t of x. And expectation of t of x is the same thing as summation of t of x times p, the probability of x. Okay. What else? Summation of t of x, probability of x, which is, you can call the PMF of x for geometric distribution, is what? 1 minus p, x minus 1 times p. And we know q is the same thing as 1 minus p. So this can be written as summation of t of x times q raised by x minus 1 times p. So if you look at it very well, what did you notice? This can be rewritten as summation of t of x times q of x over q. How do we achieve this? Times p, don't forget. How do we achieve this? Hope you know that q, from rule of indices, you know that when you have qx divided by q raised by minus 1, hope you know it's the same thing as q the same thing as qx minus 1. The same way when you have qx times this, is the same thing as q plus 1. So that is why when you have qx minus 1, you can rewrite it as qx divided by q raised by 1. But don't forget this one, there's no need to show it. It's only when you have it in this form that you need to show it. So that's how the That's what they did here. Okay, so since these are constants, you can bring this out. P over Q for summation of T of X, Q raised to X. Now, if you look at this in very well, both of them are what? Raised to X. So you can write this as TQ raised to X. Okay. Summation of X equals to 1 up to N. So since our X shows from 1, this is a geometric series. So what did we say about geometric series? In this case, our A over 1 minus R and over 1 minus R. I hope you've not forgotten. In this case, our A is also our R. So what will this become? This will become P over Q, which is outside of all of this, times what? A, which is QT, times 1 minus QT, which is our R raised to N, divided by 1 minus QT. This is Q. Sorry about that. We're almost done. So now you have G of T limit N as it tends to infinity for P of Q times QT 1 minus QT N over 1 minus QT. So since the QT must be less than 1, then our QT raised to N is equal to 0 as we approach 0. So what that simply means that all of this will now become P over Q QT 1 minus 0 over 1 minus QT. Q cancel this Q outside and you're left with PT over 1 minus QT. So this is our G of T for geometric. So by the next class, we will continue from binomial to Poisson. Then from Poisson, we'll go into the other topics. So what time is it? Okay, so it's 10 o'clock. We'll have to call it a day. Thank you for having me. Till we see you next time. Bye.